All right. How's everyone doing today? Pretty good. Okay. Was everyone able to work on their lab and get that all set up and turned in all right? Any questions before we get started? All right. So if we go to Blackboard, we can open up our class here, and I've put up the lab example we'll be doing for this week. That lab is going to be on a determinate beam. So we're going to consider the determinate beam shown in figure 1. The total length of the beam is 36 feet. And the dimensions and supports are given in the figure, and the self-weight of the beam is going to be 0. The units we're going to be using are kips, feet, and Fahrenheit. So this is a little different than last week. We're using kips and feet instead of just pounds and feet. Same material. We're going to use a W18 by 40 wide flange this week instead of the HSS section we used last week. And then we'll be performing some similar deliverables. Any questions on that? Okay, and the beam we're going to be doing, let me rotate that, zoom it out a little, is going to look like this. So we've got a simply supported beam here with a cantilever off of the one end. It's got a point load, a uniformly distributed load, and a trapezoidally distributed load. So I'll show you how to apply all of those. Any questions on this one? Okay, so let's go and bring up SAP and get this moving. Is everyone all right? Okay. So give this a minute while SAP opens up. There we go. All right. Anyone else need a minute to get SAP all the way open? I'm sorry, what was that? Okay, well, let's start working on the lab then. So first thing we're going to need to do is open a new model. Okay, now we have the new model thing. window opened up here. So the first thing we're going to need to do is set our units. So if we remember from the document on Blackboard here, we want our units to be in kips, feet, and Fahrenheit. So let's select those. That's going to be this one here, kips, feet, Fahrenheit. And then everything else is fine. And we want to select our template. Now this week we can use the beam template. So we're going to click on the beam template right here. Okay, now there's a couple boxes here, and these are useful if we have a beam that has multiple spans, and these, or just one span, and these spans are the same length. However, if we look at this beam right here, the span between these supports and our cantilever right here, none of this is the same length. So we need to do a bit of custom spacing here. So what we're going to do, instead of using these two boxes here, is go and check this box called Use Custom Grid Spacing. And then we're going to click on this button here called Edit Grid. So click on that. And we see we have a menu similar-ish to the one we were doing last week. And what this does is it goes and lets us go and create grid spacings in our X, Y, and Z axes. Now, because beams are largely one-dimensional structural shapes, so they're much longer in one axis than the other, we're not gonna need more than one line in the Y or Z axes. So these are already fine right here, but we want to kind of set a couple of these points on the X axis to correspond with these points we have on our beam here. Make sense? Okay, so what we're going to do is we're going to change how this is initially set it up to match what we have in our model here. And I'm going to start at the left end here. So at the left, I like to start at 0 because that makes adding everything up nice and easy. It's going to put our origin at the far left of the beam there, and that's nice and easy to work with. So I'll start that at 0 there. So the ordinate here is basically how far you are from the point of origin. So if we set our far left point to be 0, it's going to be there. And I'm going to change the label from A to C here to match what's in our drawing. Now the next one is going to be point D here. So I'll change this one to point D, and its ordinate is going to be 4 feet to the right of point C. Now if you remember the coordinate system we're using, right is positive X and up is Z. So we're going to be going positive 4 feet from our initial point there. So that's going to be 4 right there. Now all this other stuff is basically how it goes and displays the point markers. So we don't really need to worry about these 3 columns here. All right, so now the next one we have is point A here, and that's going to be another 4 feet over. So let's go and change that to A. And then this ordinate, it's going to be 4 plus 4 feet over. So that's going to be 8 feet. Okay, now we want to add some more columns here. So we can go and use this add button on the right to go and add some more rows into this table here, because we have more than just the 3 points. So I'll add another one here. And that's going to be our point E, and that's going to be 4 plus 4 plus 15. That should be, 23 feet. So that's going to be E there. We're going to put in 23 here. All right. Now our next point after that's going to be F, and that's going to be at 26 feet there. So we'll add another line. That's already at F, and we're going to set that to 26. And then we're going to want one more after that, point B, and that's going to be at 36 feet. Okay, any questions on how we did that or why we used those numbers? Everyone caught up? Perfect. Okay, so once we've done that, we can press OK down here. And that's gone and set up our grid spacing and our X direction for our beam. The next thing we can do, remember last week when we had to draw everything in and we had to go and apply cross-sectional property to it? Well, because this is a beam template, it's going to already go and draw in our geometry for us as a beam between those points we drew it as. And it can go and pre-apply a cross-sectional property to it when it's generating the model. So what we can do here is go and import that cross-sectional property and have it be applied by default. So if we go in our dropdown here, there's only just the default cross-sectional property. But if we use this plus button next to it, we can go and import a new cross-sectional property just like we did last week. So we're going to hit the plus button here. And it wants us to select a new frame property. Now we don't have anything in the list over here. So we're going to either need to import a new property or add one. We'll cover this one next week, but we're going to import a new property just like we did last week. So we'll click on this one, and it brings us to all of these shapes here. Now, what shape do we want to import for this? We want it to be a W18 by 40. So how we're going to do that is we are going to go down to the AISC 15 right there. And then we are going to press OK. Now, there's a lot of different wide flange or kind of eye-shaped members here. We've got all the piles, and those are the HP shapes. We've got some miscellaneous M shapes. We've got the old American Standard I-beam shapes, and those have been remarked as S. And those are from way back in the day. And then we have all the wide flange W shapes down here. So the W shape we want is W18 by 40. So we'll scroll down a bit till we get there. And we will click on 18 by 40 here. So we're about 55 or 60% of the way down the list. We'll click on W18 by 40, press OK again, and then we can press OK one more time. Make sense? Okay, and then one last thing we can do with this property here is this restraints down here. Now, by default, it's going to apply a boundary condition at every single one of these points we imported on our grid here. Now, we only want it on 2 of them, so we can come back later and turn off a whole bunch of these boundary conditions. It'll usually put in 1 pin and a whole bunch of rollers, because that's usually how you go and design a really big, long, continuous beam like this. So if you have more than 1 pins, it's not determinate anymore. Well, if you have more than 2, it's not determinate anymore. But if you have a whole bunch of pins, it's easier to analyze. Or rollers, I mean. And then it can expand and contract like it needs to. So that's how it would model it if we left this box on. But if we turn this off, it's not going to apply any of the boundary conditions, and we just need to remember to do that. So I'm going to turn it off because I think it's a little less work for us if we do that. Okay, now we've set everything up. We can press OK here. And what it's going to do is it's going to generate our beam. So we've got a 3D view here and an XZ plane view at y = 0 over here. And it's just a straight line, which is good because we want to model a beam. So I'm going to close this one real quick. And we've got our beam here. And you see we've got points CDA, EF, and B. And that's corresponding to the same points we have on our beam here, CDA, EF, and B. Okay, so let's go and add in our boundary conditions to put those in before we forget. So at point A here, we want to add in a pin, and at point B, we want a roller. So let's click on point A. We'll go to Assign, Joint, Restraints. We'll click on the pin here, then press OK. We've got our pin now. Now we'll do the same at B, except we want a roller. So we'll go to Assign, Joint, Restraints. Click on the roller here. and then press OK. So now we've got our pin here and our roller here. All right, any questions on that? Okay, let's see here. So if we want to double check what cross-section was applied to our beam, I mean, we imported and we had it in the template, so it's going to be what we want it to be. But if, say, you just want to double check it, you can either right-click on a member, and it goes and brings up all this information on it. And the very first one up here is the section property, and that's W18 by 40 here. So that's good. Or what we can do is we can go to display, and then show MISC element assignments frame. I think it's this one. Yes. Yeah, so display, show MISC element assignments, and then frame here. And then cross or section properties is highlighted there by default. We can press OK. Okay, is one of these other ones? Nope. And then it goes and shows us what all of our cross sections are assigned as right on the model there. Now, just like last week, if we don't want to necessarily be showing something, we can always get back to a default view of our model by pressing this show undeformed shape button up here. And that just brings us back to a nice clean picture of the model without any of the annotation on top of it. Okay, so that's all of the geometry done. Now we need to assign our loads. So first things first, before I forget, or almost forget like last week, let's go and turn off our self-weight, because in the example here, it says we want to consider the self-weight of the beam to be 0. Why do we want to do this? We want to do this in this case because if you were going and finding these same results by hand, we would want this analysis to match that. Because if you're doing the hand calculation results, you're probably not going and including that thin uniform load along the beam here for its self-weight, and SAP would do that. And that'll change the results ever so slightly. So to do that, same process as last week, we go to define, we go down to load patterns. We're going to be working in the dead load again this week. So we're going to change this 1 to a 0, and then press modify load pattern to save it to the dead load case here. Everyone good with that? Okay, so we'll press OK on that. And now our self-weight's turned off. Now let's add the rest of our loads as dead loads, and then we can analyze and be done. So what loads do we want? Let's see here. Let's start off simple like last week. Let's add our 25 kip point load at point D here. So we'll select our node there. Then we're going to go to assign, joint loads, forces. This is the same procedure we did last week. So it's going to be a 25 kip point load going downwards at point D here. So we're going to be in the force global Z menu right here, and we're going to put in minus 25 because our unit is in kips. And we'll press OK there. And we see we now have the 25 kip load at point D. Okay, next, let's do our uniform load here. So that's going to be on the segment FB here. So let's select that segment. And then we're going to go to assign. Then we're going to go to frame loads. And then we're going to go to distributed. So assign, frame loads, distributed. Okay, now this menu has some more stuff going on in it. Everything in the top is okay for right now, so we don't need to change that. Over here on the right, the options are okay, but for uniform load, this is what we would want to use for a uniformly distributed dead load. So how much did we want? We wanted this to be 4 kips per foot. So what this does is it goes and applies this load in the direction that's selected in this third box right here. And this third box right here defaults to gravity. And gravity is the negative z direction in SAP. So we just need to put in 4 kips here, and that will go in the negative z direction. If we put in -4 here, that's going to be going opposite of gravity, and that would be going up. So it's a little confusing. You could change this to z if you want to put in -z here. There's a whole bunch of options here, but if you just want to keep that the same, just keep this as +4 here. And then we'll press OK. And we see we have a 4 kip load pointing downwards here. Any questions on that? Yes. Very good question. So if you look in what the tab up here is called, it's called frame distributed loads. So we're only displaying the distributed loads for our dead load case right now. The point load is still there. It's just not being displayed at the moment. So when we have a whole lot of different loads being applied in SAP, if we try and display all of them simultaneously, it gets a little crazy. So what SAP will do is it's just going to try and display as few as it can at the same time. So it's still there. If we go and right click on D there, it's still got the load on there. But it's just not being displayed right now. So it's just kind of what the program does. That makes sense? Cool. Any other questions on that? Pretty straightforward for distributed loads. Cool. Okay, now let's do our last one, and that's going to be the trapezoidally distributed load between points A and E. So it's going to start at 2 kips per foot at A and go to 10 kips per foot at E. So let's select that segment of our beam here. And then we're going to go to Assign, Frame Loads, Distributed. So the same thing we went to for the uniform load, but instead of using the uniform load box here, we're going to use these trapezoidal load boxes down here. Now, before we get down to those, let's not forget we want to set the uniform load back to 0. Otherwise, if we just go and do our thing down here, it's going to add that load plus another distributed load of 4 kips per foot here. And because of superposition, that's going to be way more load than we actually want there. So we're going to set that back to 0 so we're not adding loads we don't want to be there. Okay, now in trapezoidal loads here, what we do is we have these relative distances from the end. So this is a fraction between 0 and 1. And at those relative distances, we can put an intensity of the distributed load. So this is good for all sorts of types of trapezoidal loads here, depending on how you want to do your trapezoid. In this case, it's a pretty simple one. We only have 2 points to kind of linearly go between the start and the end. If we have a couple points in the middle, we have the extra boxes for those 2. But we only need to use 2 of these columns right now to do this. I think in your assignment, I've got it using all 4 of them. So you just go from left to right with the relative distance here as the fraction between 0 and 1, and then you'd go and put in the corresponding intensity of the load there. Okay, so we're going to start at the left here and go to the right. All the way at the left here, that's going to be a relative distance of 0 along this segment of the beam here. And it's going to start with 2 kips per foot. So at the very left here, we're going to start with 0, and we're going to have a load of 2 kips per foot starting right here. And then our next point of interest is all the way at the end of the beam here, where we end up at 10 kips per foot all the way at the end. So that would be a relative distance of 1, and we would go and plug in 10 kips per foot. And then we have these extra boxes over here, so just set those all to 0. Does that make sense? Now, if your fractions are really weird, you can also change it from relative distance to absolute distance, and you could put in the number of feet it is from one point to the next. I usually like doing relative distance though. That's just my preference though. You can do it either way. Okay, so now that we have that 0, 1, and then 2, 10, and then everything else is zeros, we can press OK. And we see we have our trapezoidal load here, and it starts at 2, and then it goes all the way up to 10 here. Make sense? Awesome. Okay, and that's all of our loads we have. So now we can analyze our model. So let's run it. We're going to not run our modal case, just like last week. We'll say run now. It's going to ask us to save it. So I'm going to make myself a new folder. We'll save it. It's going to take just a second to run. And then we can press done here. And we've got our deformed shape of our beam here. So we see kind of in that simply supported section, it bows downwards. And because there's enough load in there, that manages to kind of pop up that cantilever, even though we do have a point load acting on it. So this is the deformed shape of our beam here. So let's look at our deliverables we want to do for this week and show you how to get to those. So the first one here is going to be the reactions for each support with values and arrows, and we'll do that the same way we did last week. So to do that, we go to display, show forces, stresses, and joints. Click on that. All of these are good by default, so we can press OK here. And here we go and get our reactions. Now, we didn't apply any loads with a component in the x direction, so it makes sense that on our pin here, we don't have an x component. So we only have the 2 vertical components here. And if you go and check the equilibrium by hand, you can go and verify these numbers for yourself based off of those loads. Okay. The next one we want is the deformed shape. So let's go and do that. We can also use these shortcuts over here to get to some of these menus. So in display, we've got show deformed shape and show forces and stresses. And there's also the show undeformed shape up here. These 3 shortcuts do the same thing. So sometimes I might just go to these instead of going through the file. But to show deformed shape there, I'll just turn on the wire shadow and press OK. And we see our deformed shape here. So we can take a screenshot of that for the report. Okay, and then we want the deflection at point F. Now, which point was F? That's going to be this one at it's the second rightmost point here. Now, we can kind of try and pixel hunt our way along the beam here, but an easier way I've found to do that is to go and just select a bit here to go and see where that point actually ends instead of just trying to scrub our way along the beam until we find it. So you can see if we select it, we've got this little selection line here and the points at that end. So there we've got the vertical displacement as minus 0.266 feet. So that's about 3-ish inches. So probably a little much for this beam. That's a lot of load on it.
From your deformed shape, you can drag and highlight that?
Yeah. So you can highlight these in the deformed shape here. The highlights aren't going to follow the shape of the deformed curve because this is kind of using a cubic curve to interpolate between those points based off of how they deform and rotate. But if you're having trouble finding these points, you can go and select parts of the model to actually go and figure out where the point is. Does that make sense? Yeah. So that's the information we're looking for there. Now, to get these deformation values from these specific points, you need to be in the deformed shape to go and find those. There's other ways, but you need to go in like export tables and stuff too, and this is just the easier way to do it. Okay. Any questions on that? Everyone good? Yeah.
Hover over it, yeah, set value.
Yeah.
Then when you double click,
Yeah, when you right click on it, that's what it is on Windows. I'm not quite sure what the Mac OS equivalent would be.
that one has a higher resolution accuracies.
It's got it doesn't matter. You're usually not working to 4 or 5 sig figs of accuracy and deflections. So either one's fine. Yeah. As you'll see when we get to the deflections portion of this class, deflection models they use a couple approximations. So when we're doing these analyses, these are pretty accurate, but they're not 5 sig figs accurate or 5 decimal places accurate here. So this is going to give us a pretty good estimate of what our deflection is going to be, but that last decimal place isn't going to matter. Okay. Any questions on this? Everyone good with all that? Okay, cool. So the next one we want is our shear diagram with values. So to go to that, we go to display, show forces, stresses, frames, cables, tendons. If you remember, this is where we went for our axial diagram and our moment diagram last week. Now, instead of going to those, what we're going to do is click on shear 2-2. And then instead of fill diagram, we're going to say show diagram. So we actually have numbers on there. And then we can press OK. And that will give us our shear diagram. So blue is positive, red is negative, and the numbers on there are kind of the extreme points on those graphs. So if you see, we've got a constant on the shear diagram here and here. We've got a linear portion there, and this in here should be a quadratic portion of the curve. Now, if that's ever a little too confusing, what we can do is when we're making our model, we can assign more output stations. So if it's a property in the frames here, and that basically just forces the program to go and compute the points along the beam closer together than the spacing right here. And that can get you much nicer diagrams there if you need them. These, in 95% of cases, are more than sufficient. What we can also do when we have stuff like this is right-click on the beam, and this goes and gives us some information on each of those beam segments there. So we see this one is flashing right here, and that's our shear diagram. A little bit of a preview of our moment diagram there. And stuff like that. Any questions on that? So this would be the shear diagram. You just want to take a picture of that for the report there. And then same procedure for the moment diagram here. To get to that, we'd go to display, show forces, stresses, frames, cables, tendons. And then instead of shear 2-2, we click on moment 3-3. And then we press OK. And then we get our moment diagram. All right, any questions on that? Okay, I'll just note real quick, if you're going and plotting this out by hand as well, you might notice, hey, wait a minute, this moment diagram's flipped upside down from how we were taught to do it here. That's because people go and have different conventions for drawing moment diagrams, and it's really confusing. And I like our way better, but it is what it is. This is more of the international or European style of doing it. They go and flip the moment diagram so that kind of matches the curvature of the deflection a little better. There are benefits to it, but then you're introducing signs in your integration to go and get these diagrams. So if you want it a specific way, if you don't care if it's this way or if you need it in the other way, there's an option up here in options where we can turn off moment diagrams on tension side, and it'll flip it to something you might be more used to. So if you need to flip it, that's how you do it. But it doesn't matter either way you do it. So don't worry. Okay, and that's all the deliverables for this lab. So any questions on this one? Hopefully pretty straightforward. Cool. Well, thanks for coming to lab this week. For sure.